Okay, let's get serious now. What is quantum computing? To answer this question, we need to look at the differences between quantum computing and classical computing. Now, in classical computing, we represent information using ones and zeros in what's called a bit. However, in quantum computing, we use a special type of bit called a qubit, which can represent a 1 and a 0 at the same time. Okay, let's take a group of 8 people, each one of which are going to be represented by a binary number. Now, let's take this group of people and go get some ice cream. Now, our ice cream seller is a little bit strange. You see, on some days he'll give the entire group double scoops of ice cream, but on other days he'll only give half the group double scoops of ice cream. What we want to know is if it's a good day for ice cream. Will the entire group get double scoops or not? Now, if we were to look at the number of steps it will take for us to solve this problem using a classical computer, you'll quickly see the difference and why quantum computers are far more powerful. You see, it takes a maximum of 5 steps in order to determine with a classical computer if the entire group is getting double scoops or only half. This is because we would have to look at a minimum of 5 people in order to work out if it's a double scoops for every one day or not. Here comes the crazy part. With a quantum computer, we only need to make one observation. But how can this be so, I hear you cry? Well, think back to our classical computer. We would have to look at each individual person to realise if they're a 1 or a 0, a double scoop or a single scoop. Yet in quantum computing, we can be clever and look at the entire group as a whole. If you remember earlier, I mentioned how qubits are different from normal bits. In a regular bit, you either have a 1 or a 0, yet with qubits, they can be a 1 and a 0 at the same time. They also have the unique property of being able to interact with each other, meaning that we can look at this problem not as individual people, but as an entire group at once in order to determine an answer. However, Heisenberg's uncertainty principle trips us up. Picture the group as a set of cards. However, it's a very unique set of cards that whenever we turn around and look at it, it instantly collapses down into a pile. Now, if we are clever and make our pile of cards in the correct way, then when we look at the collapsed pile of cards on the floor, we can look at it and make a guess as to the original shape of the deck of cards. We can apply this principle to our ice cream problem in order to make a single observation and then work out if it's a double ice cream day or if only half our group will be receiving 2 scoops. Let's make a quick recap of what we looked at so far. First of all, a qubit can represent a 1 and a 0 at the same time. 2. We can observe a group to learn about the characteristics of its contents. 3. This process is made difficult as we cannot observe the group directly, only make a guess about its characteristics from what we can observe from its collapsed form. The more quantum bits we add to our quantum computer, the more powerful it becomes. This increase of energy is thought to be exponential, so adding single qubits is much more effective than with classical computing. Thanks for watching. If you liked it, be sure to click the like button down below, and if you really liked it, consider subscribing to the channel. I'm looking to make more of these videos in the future, so make sure to click the bell icon so you'll be the first to know.